Hi guys, welcome to today's session of the Data Science Mentor cohort. And today our focus is on the last part of the support vector machine series. But before we get started, my name is Pablo. I am a data science professional. I am also an aspiring cloud professional. The whole idea for the Data Science Mentor program is to help people learn data science from scratch using examples and mentorship. There's a whole lot in the that leads up to learning data science, and it is super important that learners pick up these examples and mentorship as we proceed. Right. So I'm the host, founder, and the convener of the Data Science Mentor program, and we're getting started as quick as possible. Today we're looking at tuning support vector machines. Now, this is going to be the final part of what we are doing for support vector machines. And today's intuition, we're going to be looking at what would happen if we were to look at a data set that's all over the place. Again, we're going to build this data ourselves, and we're going to write code to do it, and then we're going to finish up on that part. What happens? We have looked at data that are non-linear. So how do you use boundaries? How do you create boundaries that classify the data? We have looked at linear data, and it's been possible for us to use margins to make sense of them. So today we're going to look at data that overlaps, right? So that's why I say data that is all over the place. And also, and it's something pretty simple. When data overlaps, you typically tune your support vector machine. So that's what it is. So again, the intuition for today, I'm going to look at it. We're going to be looking at a few intuitions. We're going to be looking at a few intuitions. Now, the first is going to be data that overlaps. Now, data that overlaps could also be unclean data, so to speak. Is that enough? Right, because the data that overlaps, for the most part, makes creating decision boundaries pretty difficult, right? So this data isn't perfect for decision boundaries. It isn't perfect for decision boundaries. So this what we're going to be looking at, right? So how do we work with this? Now, it's super important that when you build models or you think around building models, that it is that you think about different edge cases. And today's edge cases is data that overlaps or data that isn't perfect for decision boundaries. So the first thing we'll do is to visualize the data we have. Also, if this is your first time, we're going to be looking at data we're going to create the data ourselves. We're going to use data from the sklearn data science data sets repository. So that's what we're going to be using. So to get started, we would start off by saying X and Y. Again, remember, X and Y representation of a feature matrix and target vectors, because we're looking at this scikit-learn estimator, and that's how the data representation happens, right? So now we're going to take make blobs. Now I put the make blobs without importing the model class from which will import make blobs. Why? Because I've done that in the other series. So if this is your first series, please check out the other series. If it should be in your resource pack. So if you're signed up to the Data Science Mentor program, you should have that in your resource pack. right? If you are watching the live session, if this is made live, you can check out the sklearn um, documentation. You're going to see sklearn.datasets that would work. So make blobs. Now with make blobs, we could use, again, it's ideal for us to check out our documentation. So we could generate blobs. It's basically blob for clustering, but it makes perfect sense for a learning experience. Now, the idea here will be that we'll create n_samples, and we're going to create 100 of these blobs. We're going to create a center here, just 2, and we're going to call on our random states. So this makes it easy for us to reproduce. We'll also call on a cluster STD, which means we create clusters and we create a standard deviation for it. And and standard deviation basically it's the intuition behind how tightly knit data is or how spread out it is. So we'll put 1.2. Okay, let's make it 1.2. Now we've got this. Now that we have this, the next thing we would want to do to understand what this is to visualize the data. Now I'm just going to do a simple visualization using Matplotlib. Again, I have had that imported into the namespace. So you can see if I say plt dots, you can see that I already have that in my namespace. By the way, what I used to make that come out is as the tab. So once you just put that out, put the dots and hit the tab, it all comes out. So what I want to do is a scatter plot. I'm going to put out a scatter plot. Now I am going to divide the data we've created from make blobs, which are like tiny circles. I want to divide them into 2. So we're going to have them in 2 places. And because it's X and Y, I'm going to have to separate them, but I'll also make them overlap because that's the idea. So the first thing I'll do is, since I have X here already, you can see X.shape. So it's 100 samples, 2 features. And you can see that it's in 2 dimensions. I could bring it over here and I say X, then I will slice. I'll create a slice. The first slice creates for our first dimension, and then the second slice will create for the second dimension. So with this, we already have data circles that are separated. Then we are going to determine the separation using Y, and we have S here for 50, sort of like size. S, then we have a color map, and we use autumn. Now, if you're watching this for the first time and you're saying, why did you take a color map and bring out autumn? Why that? You could use anything. If you do a simple Google search for Matplotlib's color map, you're going to see a bunch of color maps, but I'm not going to do it here because that's not the focus. If you're interested in this, check out our introduction to data visualization or data science. We have a lot of conversation on that. So that's there. So we have this. So the next I'm going to do is plt.show. And let me see if this works. This should work. Now you can see that now some of the data points, let me make this, let me reduce this so you can see. You can see that some of the data points sort of overlap. If you see over here, you can see some overlapping. Now, I'm going to now show you some context. You can see that around here, we didn't really have overlapping data. You can see this sort of like spaces here. Even though this one is different, we didn't have overlapping data. If I step back here, even when we looked at the 3D, a 3D visualization of the same data, they were not overlapping. And now we go back to this again and again, you can see there was sort of like a way for a decision boundary to be created. And of course, you can see the way the support vectors all like pitched on which ones where the where the boundaries are. Now, but what if your data isn't that way? If your data isn't that way, then you have this situation here. Now, how do you deal with this? Now, a simple way to look at it or to handle this SVN implementation is, I mean, it feels like it's like you need to like look at your margins and soften them in a way, so which will allow allow a little bit of creeping through with overlapping margins, and which will allow for a better fit. Now, the margins would have to be softened, and the only way to soften this margin is to tune your parameter. So that's why if you look at it, it's called tuning. You're going to tune your parameter. Now, what is responsible for tuning your parameter? Let me bring this back again. So what we're going to do so that we can deal with this overlap, with these overlaps here, is we tune our parameter. So this is what we're going to do. We're going to tune our parameter. So now when we tune this parameter, we are going to, there's an interesting parameter tuning we're going to look at. So let's just come over here. See, we already have the support vector machine. So let's look at this. Call this SVC. So we have SVC, right? And if I was to put this inside and check out SVC, say I'm calling, oh shoot, oh look at that, I said SVC, and I put this, you can see that there's something called a C. Look at this C over here. So we're going to look at what C is about. Now, C is a regularization parameter, which typically regularization is like a very intuitive way of thinking of regularization is, what do you do to yourself to prevent yourself from overthinking things? Say you applied for maybe your master's in maybe an American university, and before applying for the master's, you start to overthink the application process. Then you start to do too many things. When you regularize, you sort of tell yourself to calm down. Sort of like you punish your overthinking. That's what regularization does. Now, you can see here, it says the strength of the regularization is inversely proportional to the C. And it must be strictly positive. The penalty is a squared L2 penalty. Now, that's a different conversation. But what it does is, if we find a way to have the C, right? What the C does is it makes us, it sort of like softens the lines that we're working on. Now, what we're going to do is we are going to find different C values. We're going to use different C values for this. And with different C values, we can now see how well we can soften our way through our overlapped data. So that's what we're going to do for this. Now, to make this possible, what I'm going to do is I'm going to rewrite the code we already have, and I am going to this time I'm going to reduce, I'll sort of reduce the standard deviation, create a new figure so that we can see we're going to have two plots inside of it. And we're going to see how both of them works when we have two different C values. So that way you're going to see the softening of these margins and how the support vectors work differently. Now remember, the idea is not the pop culture of repeating stuff. The idea is, if we had data, say email, and we needed to draw lines across this email because the data overlaps, we have emails that look like spam, but they're not spam. They sort of like take, like, sometimes you receive emails and you say your bank sends you emails. They come consistently. And sometimes when they come, they sort of have, they have sort of that thing that looks like it's a spam, right? It's colored all over, it's dropped consistently. You're not expected to reply sometimes. The emails don't look like the regular type email you would receive, the regular type email addresses. And sometimes the model that classifies spam or no spam sometimes might misclassify them as um, spam. Now, this is a situation where we now have to tune our C, which is punish that overthinking that the model is doing in case where we have overlapping data. So that's like a real life intuition of what we're looking at. So first thing, we are going to now recreate the blob that we created before, but this time around, we're going to make changes to it. So I'll copy this. Makes it easy for me to do. Now, the difference here is we are going to change this to 0.8. We're going to give it the lower standard deviation, sort of maybe so that we could see as this overlap works, right? And so we can, we can see where the levels of overlap work. So it's not too clustered, but we can see the idea that we're trying to work on. Now, the next I'm going to do is I'm now going to use a different kind of visual. I'm going to create an object for my visual. So this is an object-oriented visualization I'm going to do. So first thing, I'm going to say fig and act, which is our objects. We're going to say subplots here. You can see that that's what we're trying to do, create a figure and set the subplots. Then what I'm going to do, I'm going to have 1 and 2. And for 1 and 2 figure, we're going to have our fig size. And our fig size is going to be a tuple containing the size. So we're going to have, it's going to be really long. So it's going to be like this, but really not so big, so that we can see the two things we're working with. Now we're going to say fig, which is our figure, and we're going to say our subplots, and then we would adjust some of the subplots. Now, I already have this set up, so which makes it pretty easy for us to set up our subplots. So you can try this out, and you could create your subplots and do so many adjustments to the right and left, and to the width space on your own. But I'll do this. So here with this, we will have our left, and in our left, I'm going to go 0.06. Then in our right, I am going to go 0.95, and then maybe say our width space, which is 0.1. Right. Next, I'm now going to remember that we have a plot. Don't forget this. Remember, we have our plot function. This is what our plot function is. So I'm going to make use of the plot function. So when you see this and you're wondering, where's this plot function coming from? It means we have done this before. So you need to check out what we've done before. So yeah, so this is what we have. Next, we're going to say for I already have, I wanted to say for x, let me put x, right? Then we're going to say C is what we're interested in. So C in zip, open brackets, because I'm going to now make a focus on this. We're later going to now, because we're going to have like a couple of axis. So I just basically use this. Now I'm going to now say the C. Remember when I mentioned I came here and I called the support vector here, and you see the C. So we're going to have a list of the C's, and so it's going to run through that. So that's what I'm going to use the C over here. And here I'm going to have a square, I'm going to have a list, and it's going to be 10 and yeah, 10.0, and we have 0.1. So these are two C parameters, like regularization parameters. And yes, so we now say we call on the model, and our model is our SVC, just like we have done earlier on here. Then inside of this, no, what did I just do? Sorry. Okay, that's different. So SVC, which is our model, it's like model instantiation. And in our model instantiation, we're going to call kernel. We're going to make it linear because it's not radial. Remember that? So it's not a basis function. So we're going to say our kernel is going to be linear. Then we're not going to say our C, because remember, we're going to look at C here. So when we say C, we're going to reference this C over here. So we're going to say our C is this C. Then we'll go on to fit our X and Y, which is what we have over here. These are data. Now we're now going to say X, which is this guy, which is the plot we're going to have. They're going to be scatter plots. That's what it's going to be. Now, remember, we're going to split the data into two places. And just like we've done here, so I'm just going to, yes, I'm going to copy this. So we don't have to, go through this again. I'll copy this. We're going to split it into two places. X, yes, Y, yes, S, and we're going to have that. Right, so, and that's one. Now, the next we want to do is we're now going to introduce our plot function. Now, remember, our plot function will take a model and it will take access, which is going to be this. So with all this, we have our data, we have our objects for visualization, which is going to show us two plots with this figure of 16 by 6, right? Yeah, so we adjusted the plots. We are also going to have our axis, which is going to be our two plots. Now, for the plots we're going to create inside, which is this, what we have here, we're going to look at two C values. And the C is going to be what we would use to understand the overlap in our data. Because just like I mentioned earlier, it's going to penalize the overthinking of the model when it sees overlapping features. And remember, the overthinking is similar to the situation where the model overthinks the email you have and then classifies an email as spam when it's not. Maybe you signed up for a newsletter, but that's not a spam because you want to read from maybe an author or something. So, and then it starts to think, okay, this is spam. Right, so stuff like that. So I'll run this. Now we already have a plot existing, right? Or do we? Oh no, that was I spoke too soon. No. So the next thing we want to do, because if we have this plot, let me see, plt.show. Let me see. Now, if we have this plot, you can see what we have here. Right. Now, this is what we have here. Now, you can see that there's a bunch, it's not complete because we don't know what is going on between these two features, but you can see the overlapping, it sort of tries to do some overlapping. But which C do we have here? Which is this? Which one does a great job? This or this? But the only way we can find out is for us to continue our work here. So what I'm going to do is I am going to, we're going to say access dot scatter. Now here we're going to say, we're going to call our model dot support vectors. This is the model support vectors. So support, I have to write that. And if I make a mistake, we'll check it out later. Vectors underscore, yes. And then we're going to look at the first set of vectors from the first data points, the first division. Then we have this, and so this is what we have here. Then I copy this, and then here we put 1, right? And that's a comma. No, I'm not going to put a comma here. So I would now have S equals to 300, 300. Size will be different. Then we have LW equals to 1, and we will now have face colors, actually colors is equal to none. Now the interesting part of what we are working with here is, let's close this. And then the next part is we will set the title. So we should set xx dot set title, set underscore title, yes. Now this, I'm now going to determine where the C is, because when I showed you guys here, you guys didn't know which is it. So we're going to determine where the C is. So here we say the first C is going to be equal to, here we're going to say 0 old mean dot 1 F, and then we'll close this. So let me make this I'm thinking how I can put this. Yes, no. I'm thinking of how I can put this. Yeah, so I can make this. Let me close this. Then I'll put a comma here, and I'll say, I'll put a comma here, and I'll say size equals to 14. I feel like something is missing here, but I am going ahead to call this. Did I get it right? Oh, you can see. Oh, what did I miss out on this? Why is it showing this? It's not so. Oh, I see where it is. F, the F string over here. Put an F, and then we'll run this again. And then it's going to show us. Uh-oh, it's taking too long. Why is it taking too long? The invalid formats. Did I put a comma there? Dots. All right, we'll run this again, and we'll run this. Okay, so we did it twice again. So let's run this so that it just overrides the existing one. So we bring this. So now you see, uh-oh, there's still 0 and 0. We need to indicate stuff for the C. We need to indicate stuff for our C. You know what I'm going to do? I'm going to do it the old school way. I'm going to do it the old school way because I'm sort of, at this point, maybe I'm getting a freeze. So what I'll do, the old school way is to basically call this And guys, there's you can use the string, but I think at this point I'm having a brain freeze, right? Then I will close this, and then I'll say dot format. This is the yeah, and then I'll call on the C, right? I'll call on the C, and I can now say comma size equals 14. This should work. I call on this, I call this. Now you can see what we have here. So this is C. This is basically what the C looks like. So this is when we say SVC, and then here we call on the C, and there's a C that is 0.1, and there's a C that is 10. Now, you can when we talked about it here, the C here tells us that is the strength of the regularization, which is the thing that penalizes overthinking, right? I use overthinking as an intuitive way of explaining it, because sometimes your model can overthink. And think of yourself, if you overthink a lot, what do you tell yourself to stop overthinking? So this is what the C's role is, right? So yeah. So we sort of did the we sort of did that here, and two different ways to penalize overthinking, a large C and a small c. And this is what the large C did, right? So the large C sort of like, went in and looked at the overlapping data point itself, right? Now, if you see the way this large C is, it came over here with a data point looking this way, and then it picked out the support vectors. Now, if your data sort of has some sort of like an overlap going on with this C over here, right? You can see that it sort of goes and starts to, use too many support vectors here to say, okay, let's understand what's going on here. Right. Now, the decision to do this tells you a lot, right? If at this point, if imagine this was our email data, what it does is it draws a line here and says, look, this is the guys that determine a lot of stuff here. Now, if this is our email data, right, and it starts to capture a lot of things here and say, look, I can see that we have some stuff here. We have our support vector, but for some reason, it captures a lot of other things inside here and says, oh, maybe some things are going on here. And here, it's typically, tries to draw a boundary and make sense of it. Here, there seem to be so much support vectors all around. Now, the idea here is one seems to sort of like stabilize things, right? And the other seems to be picking out a lot of features, right? So again, it all depends on the data you have, and it also depends on what you're trying to solve. Right. Okay. Someone asked, what does SVC mean? SVC means this. Right. It's a support vector. So it's a support vector machine, but look at it over here. It's support vector machine, but because we're using the support vector machine to classify, it's a support vector classifier. What it is. So that's what you have here, the support vector classifier. That's what we have. So hope that answers the question. Yeah. Also, the question is, what does it also mean to tune parameters? Again, that's a very good question. Now, when you're building a machine learning model, think of it as you recognizing a face of, in the midst of, say, 50 people, right? If you think of yourself coming into a room twice, and in the first situation, you get a chance to, and in the 50 people there, some people you know, right? Now, when you first come into the room the first time, you go into the room, and the first thing you want to do is you want to be certain of the people you see before you say hi to them. So when you come into the room, well, everybody knows you're in the room, and let's say it's something as, let's say, an old, like a reunion, maybe your high school reunion, and to that end, you're just walking through and you must be sure who it is before you say hi. At a point, what your algorithm is doing is saying, look, I would check, and maybe if that's your default algorithm, there are people who are different. If that's your default algorithm, you just come into the room and you're walking, you must only say hi to people you recognize. And so the first person you might recognize is your high school best friend. But other people are in the room like, what's this person feeling like? Now, if you come into the room the second time, and this time you've done it in the first reunion, and obviously your feedback was like, what is this one? This one has become a snub, right? In the second time you're coming, you're going to tune your parameter. And so what you're going to do is, you say when you get in, you will say hi to people regardless of if you remember them. So you get in this next time, you say hi, hello, how you doing? And then maybe as you're saying hi and finding out, you just say, oh, hey, what's up with Jane? Blah, blah. So now when you tune your parameters after your first training, you tune your parameters so that your parameters can, sort of see if you can recognize patterns differently. Because every parameter inside your algorithm or your model, plays a role when it sees your data. And we talked about, parameter tuning some time back. Of course, this also means you haven't watched those videos, and that's perfectly okay. You can take your time. But when you see that, it means that when you build your model the first time, the next time you're building and you need to improve on the model you tune your parameters, and some of the parameters do different things to your data points in terms of finding patterns. So that's what it means to tune your parameters. Right, please, more questions. I think that helps to put perspective. So that's what this is. So in the grand scheme of the support vector machine, a support vector classifier that we have looked at, it's a model that enables, that can, if you have features, it can set boundaries to create gaps between the different features that exist in your data. And if it is you predicting two different classes, like a boy or a girl, right, and the data is all gathered together, the support vector machine will create something like, see them over here, it will create boundaries. They'll set boundaries, and then there'll be what they call support vectors that figure out the threshold for these boundaries to separate the different classes. So that's what it does. And this makes it easy for you to make predictions on future events based on the data you have at the moment or you have collected before, which are historical data points. All right. For further questions, please feel free to drop it. If you are live, you can see that we answered questions from folks who are live in our data science mentor session. If you're watching a recorded, okay, go ahead.
Good afternoon, sir.
Good afternoon.
I would love to know what this plot is telling us about. These two plots we have.
Okay, and now, so initially, so I'll do a quick review. I did that at the beginning of the session, right? When you build a model, at first, when you're learning how to build a model, you would use data points. Here, what we do is we generate our data points, and we try to teach you some form of an intuition for what it's doing. So in our first data points we generated, we wanted to see how the support vector classifier draws lines to separate data into classes. Now, if we go down here, or rather go up here, this was the initial data point we started out with. So you can see I started out by talking about the different data points. So we used data points, make circles or make blobs, which are data sets from scikit-learn's repository. Now, what this is, we now pretended that this is real life data and it's depicting anything. It could be emails, it could be finding out if someone will default on a loan or not. It could be acceptance, if you've been accepted into a program or not, or admission acceptance. That could be stuff like that. Now, the first thing we do is to assume that everything is equal in life, and then we'll show you how the support vector algorithm or model does this thing. But before we do that, we have to explain what if we're human beings and we try to do it ourselves. So that's what I try to do at first. But then when we fit in a support vector machine, it sort of creates, you see the support vectors that say, look at our boundary. So there's a boundary in here, and look at data points around here. These are our boundaries. And some of these vectors are the ones that keep that they're sort of like the last people you meet that says, this is the end of these data points that looks alike before we get into another class. Again, it could be predictions, it could be, different, it could be loan defaults or, paid. It could be yes or a no, it could be black or white, whatever it is you're predicting. Now, but the reality in life is our data points don't act that way all the time. It's not straightforward. It's not like linear. So sometimes our data points could turn out to be like this. So what if your data points like this? If you try to set boundaries, it doesn't really figure it out. So to that end, we sort of tune our parameter and try to see the data in 3D. Now, when we tune the parameter, we change it to a radial basis function, sort of like a radial, it sort of like looks at it round. And then what it does is that it looks at it in a different way and creates boundaries. See, look at the boundaries it created. So this time around, if your data was non-linear, if your data does not basically it's not linear, unlike this where everything is basically divided into two and looks ideal. What if your data is not and it's in a different shape? So it can typically just read into it and find different boundaries. Then we now thought to ourselves, but what if it's not in this situation and your data sort of overlaps instead of, having, being non-linear, but it overlaps. So which means some data points are all over each other or they are very close. So we showed this by showing a situation like this in the beginning of the session, right? Sometimes you see the data sort of overlaps. And that's why I mentioned maybe sometimes you have an email address, an email coming from your bank, and the email comes consistently every time. Maybe you use your app to make transactions. It tells you, oh, somebody just reached out, or it sends newsletters. It says, oh, we have a new financial product, or use this card, or buy into this card, stuff like that. Kids savers, or happy savers, or fixed savers. Banks do that. But then the algorithm that is, trying to separate these emails and classify one as spam or not spam, sort of like getting it all over the place. So how do you tune your parameter when you have data that looks like this? Now, we pointed out that there's an interesting feature called C, which is this, by default is 1. And what it does is that it does something called, it penalizes the overthinking of your model. That is what is called regularization, right? And depending on the value you put to it, it will penalize it, or sort of like makes it not to overthink, or just let it be that way. Now, with that, we use 2 parameters, right? And we use 10 and we use 0.1. And with 0.1, you can see that it captures a lot of vectors and say, oh, there's a lot going on here. And with this guy sort of like says, you know what, there's some similarities, but sort of like we can find a boundary in between. So you can see the two ways these guys perform on the same data points, but because they are tuned differently with different penalizing parameters, they'll give us two different patterns and results. So that's what you are looking at.
All right,
Questions?
thank you, sir.
Yes, you are welcome. Questions, guys? Questions? All right, so final part of this, if you are not watching this live or you are watching the recorded session, you have questions just like Grace just asked, please drop the questions in our private Telegram channel. And this will be the end of this session.